In this video, I want to talk about the chemistry of soap. Now, soap is something we use almost every single day. At least I hope you use every single day. And the chemistry behind soap and how it works is actually pretty interesting. So let's take a look at the nuts and bolts behind soap. So what is soap? Well, soap in chemistry has a particular definition, and that definition is a salt of a fatty acid. A salt of a fatty acid. Great. Now what does that mean? Well, let's break this definition down. So fatty acid is another name for a long chain carboxylic acid. A long chain carboxylic acid. But what is a carboxylic acid? Well, carboxylic acid is what we call in chemistry a functional group, and that's just an arrangement of atoms in a molecule, a particular arrangement of atoms in a molecule. So a carboxylic acid just looks like this. It's a carbon atom double bonded to an oxygen with an oxygen atom and a hydrogen atom attached to that carbon. So, well, the oxygen atom is attached to the carbon, the hydrogen atom is attached to the oxygen. And sticking off that is what we call a long chain. So a long chain. So what is that long chain? Well, that is just a string of carbon atoms, an arbitrary length of carbon atoms, and each of those carbon atoms have hydrogen atoms sticking off. So we have these hydrogen atoms saturating all of the carbons. Great. So this is the fatty acid, right? That's a fatty acid. So what is a salt of a fatty acid? Well, a salt, we know, like sodium chloride is an example of a salt. But in chemistry, what makes sodium chloride a salt? Well, a salt is anything simply with an anion and a cation, right? An anion is something with a negative charge, right? And in the case of sodium chloride, it's the chloride ion, which has this negative charge, and the cation in sodium chloride is sodium, which is a positive charge. So it doesn't have to be sodium chloride. You can have other salts like potassium chloride or calcium chloride. These are all salts. But in the case of soap, how do we make a salt of a fatty acid? Well, we have to do something called an acid-base reaction. And to do this, we have to add NaOH, sodium hydroxide. And in soap making, that's historically called lye. So when we add this, what we get is a salt. So let's see what that salt looks like. Well, it looks very, very similar to our fatty acid, except with one difference. Oops. It looks very similar except with one difference, which is this oxygen has a minus charge. The rest of the chain looks exactly the same. It is untouched in this reaction. So how does this make a salt? Well, this oxygen has a negative charge, and that becomes strongly associated with the sodium in the NaOH. And in this reaction, we also form an equivalent of water. But this right here, this complex right here, is indeed soap. So how does the structure of this soap molecule help us create something that, or how does this clean up our hands? How does this get rid of dirt and oil that we can't normally get rid of with just plain water? Well, the key is that this molecule here is what we call amphipathic. Amphipathic. And what that means is that it has a polar end. It has a polar end and a nonpolar end in the same molecule. And in the case of soap, this guy right here is the polar end, and the long chain is the nonpolar end. Cool. So why is that important? Well, the reason that's important is because in chemistry we have a mantra. We have a mantra that says like dissolves like. So like dissolves like. And this is a pretty important mantra because it holds true in a lot of cases. So if you've ever seen, if you ever had a cup of, cup with some oil at the bottom, right? And you had on top of that some water, H2O. Well, we know H2O is a polar entity. Water is a polar entity. And the oil is actually a nonpolar entity. And if you ever done this little experiment, you'll notice that the water never mixes totally with the oil. They actually remain separate. And that's why you can't get rid of the oil and the oil and dirt and grease off your hands with just plain water. You got to add some soap. So how does that help? Well, what happens is, let's say we have these oil droplets on your hands, right? We have these non-polar oil droplets on your hands, and we have soap. And I'm going to represent this amphipathic nature of soap by doing this. I'm going to have a tail, and I'm going to have a head here. And the head represents the polar region of soap, and the tail is going to represent the nonpolar region. So if that's the case, what happens when we start washing our hands? Well, what happens is the polar region starts associating strongly with this aqueous environment that we've washed our hands with. So the polar region, right, the head of this little diagram here is going to be pointed towards the outside, and the nonpolar region is going to trap all of that oil, dirt, and grease and grime all on your hands. It's going to trap it in this bubble, what we call in chemistry as a micelle. So that bubble, which is a micelle, has these polar ends sticking out. And this is the key of soap, and what makes it so special is that now what we can do is just add water to this equation. We'll add some more water and just rinse it away. And the reason this can be rinsed away is because these polar regions get associated with that water, and the whole complex becomes solubilized. So the grease and the grime that we couldn't get rid of before is now trapped in this micelle and easily washed away by water. And that's why soap is such an amazing molecule. It has a very simple structure, but it can do so many things, like wash these nonpolar things away that we can normally get rid of. And it's been used for hundreds and hundreds of years. And all soaps pretty much work in this manner. There aren't really any other tricks up their sleeve. They pretty much have this amphipathic nature about them and get to work. So I hope that helped. I do want to post one link about how to see why certain molecules are polar and non-polar. There's a great video on that. So I'll post a link about that. But other than that, that should be about it. So I hope that helped, and